Welcome back, everyone. We are going to start Unit 2 today, and really this first lesson of Unit 2 is an intro lesson to the overarching topic of this unit, and that is a polynomial. So a polynomial, as it says here, is simply a mathematical expression that has more than one term. This prefix, poly, means many. So any expression that has more than one term is known as a polynomial. So there's different types of polynomials. We could have a binomial with bi meaning two. We could have a trinomial with tri meaning three terms, so on and so forth. But I just lump all of those together into one expression called a polynomial. And a polynomial can be used to model many different real-world situations. This particular situation that we're going to look at today is the idea of modeling the volume of an open top box. And we have the formula here that allows us to figure out what that volume is. The way it works is if you can imagine taking a standard rectangular piece of paper, rectangular shaped piece of paper, and then you cut out the same size square from each corner, and then fold up the sides, you have an open top box. And this function allows us to figure out the volume of that box. The other thing we're going to talk about today is something called the domain of a polynomial or a function. The domain is the set of all the input or x values that make sense in context. You're going to hear me use the phrase reasonable domain. What is a reasonable domain for a particular situation? And we're going to learn how to do that through this concept of the volume of an open top box. And I will explain to you how these steps work when we do the examples. So that's the lesson notes for this first lesson here. Let's go ahead and go to the examples. So, imagine constructing an open top box from a standard 8.5 inch by 11 inch sheet of paper by cutting out the same size square x from each corner and then folding up the sides. The volume v of x in cubic inches of the open top box is a function of the side length x in inches of the square cutouts. Write a polynomial expression for v of x. So to do that, I'm going to go to the formula that was given in the lesson notes. That's this formula right here. So L, or length minus 2x, times W, or width minus 2x, times x. So I'm going to rewrite that formula and fill it in. So it's L minus 2x times W minus 2x times x. So I just need to fill in the length and the width. Now notice it says in smaller print over here that we're going to assume that the length is the shorter side of the rectangle and the width is the longer side of the rectangle. So in the case of this piece of paper, which is 8.5 by 11, we're going to let 8.5 be the length, and we're going to let 11 be the width. So I'm going to plug in those numbers for L and W respectively. So that will give me 8.5 minus 2x times 11 minus 2x times x. So to answer the question, write a polynomial expression for v of x. This right here is your polynomial expression. It clearly has more than one term. And the way this polynomial works is I can figure out the volume of the box simply based on the size of the square that I cut out. So if I was cutting out a 1/4 inch by 1/4 inch sized square from each corner, of the paper, I would plug in 0.25 for x. If I was going to cut out a ½ inch by ½ inch square from each quarter, I would plug in 0.5 for x, so on and so forth. So that's number one. Number two, use Desmos to create a graph of your equation. Use that to find a reasonable domain for this equation. So we're going to graph this equation here that I did in number one. We're going to graph that on Desmos. So if you're using a computer, you can just go to desmos.com. If you're using a smartphone or a tablet, there's a Desmos graphing calculator app that you can download. That's what I'm going to use on my tablet here. So this is the Desmos app. This is what it looks like. So what I'm going to do is I'm going to put in that function that we got from number one. So it was 8.5 minus 2x times 11 minus 2 times x times x. So I'm going to graph that, and what I want to do is I'm going to mess with the graphing window in order to get a decent view of the graph. So if I want to mess with the graphing window, I can click on the wrench here, the settings, and I'm just going to kind of mess around, and you can do this on your calculator too. Okay. And then the y-axis. So I just kind of messed around with the window, and I got this wavy shaped graph here. Okay, so this is my graph. So I did that first part on Desmos. Now I'm going to use that graph to find a reasonable domain for this equation. So to do that, let's go back to the lesson notes and look at the steps. To find reasonable domain, graph the function in Desmos. We already did that. Find the 2 points that are x-intercepts. So an x-intercept is a point where the graph crosses the x-axis. So find the 2 points that are x-intercepts and where the graph is positive between them. So find the 2 points that are x-intercepts and where the graph is positive between them. The reasonable domain is between those 2 points. So let's go back to my graph here. So x-intercepts are going to be down here. So you can see, if I click on these, I have 3 different x-intercepts here. Now I'm going to look for the 2 x-intercepts where the graph is positive between them. So if I, for example, were to pick this point and this point, these two would not work because the graph is negative between them. But if I were to pick this point and this point, we can see the graph is clearly entirely positive between them. So according to the notes, the reasonable domain would be between 0 and 4.25. So to answer the question, use that to find a reasonable domain for this equation. The reasonable domain would be between 0 and 4.25 inches. And that is your answer for number 2. All right. Number 3, how would the polynomial expression for v of x change if the size of the original paper were 12 by 18? So this right here was my equation, my polynomial, when I had an 8.5 by 11. What if I changed it to 12 by 18? What do you think is the only thing that's going to change? It's the two numbers that are in blue here. So the equation, instead of being 8.5 minus 2x, is going to be 12 minus 2x. And instead of being 11 minus 2x, it's going to be 18 minus 2x. Other than that, the equation is exactly the same. The only thing that changed are the dimensions of the paper. Instead of 8.5 by 11, it was 12 by 18. So this would be my new equation. Number 4, what would the reasonable domain of that new polynomial expression be? So now I'm going to go to Desmos, and I'm going to change. I'm going to change it to 12, and what was it, 18? 12 by 18? Yes, it was. So we can see that changes the graph, so I'm just going to zoom out. I'm going to keep zooming out here. Okay, so that's not the best view, so I'm going to go to the wrench, and I'm now going to change the settings. I'm going to change the window. So let's make this from -5 to 15, and we'll say this is from -70 to 250. And that's a much better view. So you can see that it clearly has that same wavy shape. So if I were to look for, again, I'm looking for two x-intercepts where the graph is positive between them. Well, that's going to be this one right here and this one right here. The graph is clearly entirely positive between those two x-intercepts. So we would say that the reasonable domain is between 0 and 6. Okay, 0 and 6 inches. So number 4, what would the reasonable domain of that new polynomial expression be? The reasonable domain would be between 0 and 6 inches. Between 0 and 6 inches. And that is it for Unit 2, Lesson 1.